In this video, we're going to talk about definite integration. And in order to do that, we need to remind ourselves what the indefinite integral or antiderivative is. So let's draw two graphs. One graph is going to be f of x. And let's say f of x is lowercase f of x is 2x plus 3. Let's graph that. Start at 3, have a constant slope of 2, so it's a straight line. Boom. Now, if I was to take the area under the curve, so between the function and the x-axis, that area is going to tell me about the change in some original function we'll call capital f of x. And if I take the antiderivative, the indefinite integral, I get that area. So if I take the antiderivative of f of x, I'm going to get that area, or that integral, that indefinite integral. So what that would look like is the indefinite integral of 2x plus 3 is x squared plus 3x. Okay, so this is the indefinite integral. Now remember that the way that we can write this, instead of delta, we can say f of x minus f of 0. Because basically what we're trying to say is adding the function, the new function, capital F, when x is 0 to the right, reminds me that there is some unknown position, f of 0, that our new function, capital F, is going to start at, that I cannot know what it is by anti-deriving. It's more commonly called c, the constant of integration, so plus c. So we could also write it that way. Okay. So if I was to write this over here, f of x equals x squared plus 3x plus c, and then I'll get rid of all of this stuff. I should be able to take the derivative of that, right, which tells me about the slope. Should be able to take the derivative of that function with respect to x and get my lowercase f function, which is true, because if I take the derivative of x squared plus 3x plus c, I'm going to get 2x plus 3. The c goes away because it's a constant. Okay, so that's indefinite integration. If I was going to graph this capital F function, I know that it would start at c, some value. It would have an initial slope of 3. And then the positiveness of the a term in front of that x squared means it would have some smiley face to it, something like that. Who knows? Okay, so this is how the derivative and the antiderivative, they work together. The slope of one function is the derivative, and the area of that function is the antiderivative. They're sort of inverse functions of one another. The indefinite integral is super useful, but it gives us an equation. And I can use that equation, but I can only get a value from that equation if I know what c is. So it gives us an equation, but we have to be told c. So we don't know c. For indefinite integration, we get an equation, but we don't know what c is. So definite integration is this cool way of using the indefinite integral and getting a value that you don't ever need to know what c was to get. So here's how the definite integral works. Let's find the value of capital F of x at 2. Okay, so the value of capital F of x at 2 would be 2 squared plus 3 times 2 plus c. So 4 plus 6, or 10, plus c. Then let's find the value of capital F at 1. 1 squared plus 3 times 1 plus c, or 4 plus c. Okay, so we just used this function that we indefinitely integrated to get, and we plugged in numbers 2 and 1, even though we don't know what c is, because we weren't told what it is. We started with 2x plus 3. Sorry, we started with 2x plus 3, and we got to x squared plus 3x plus c. We have no way of knowing what c is. Awesome. Well, if I think about what this 10 plus c and the 4 plus c is telling me on my lowercase function f of x, it's telling me the area at those points, right? So the area of delta f of x, which would be capital F of 2 minus capital F of 1. What that is would be like saying, let's take the area underneath this function up to 2. Then let's take the area up to 1 and subtract it. What we're left with is this area between 1 and 2. And if I take f of 2, or 10 plus c, and I subtract f of 1, or 4 plus c, then I'm going to get, sorry, I should do that in parentheses, 10 plus c minus 4 minus c. And whatever that constant of integration was, it canceled out. And I'm going to get 10 minus 4, or 6. So now I know the change in f, the capital F, from 2 to 1 is 6, or this area is definitely 6. Another way of thinking about that is saying, I don't know what c is, but I do know here, where I've got f of 1, and here, we'll change it a little bit, where I have f of 2, whatever that value is. I don't know what either of those values will be, but I do know the change in the value is 6. So this is called definite integration, because you are getting a definite change in the original function. The way that we write this notation is that we say the change in some value we call capital F of x is equal to the integral of some function lowercase f of x, and we find that change from one number to another. So we call these the bounds of our integration, and there is an upper and a lower bound. In this problem that we did together, we would say 2 was our upper bound. We call that b. And 1 was our lower bound. We call that a. On our integral, we would say b is the upper and a is the lower. Okay, so the change in f of x, capital F of x, is equal to the integral of some lowercase function f of x from a to b. That's how you would read that. Of course, to denote that this change in capital F is from a to b, we normally wouldn't write delta capital F. Instead, we would write capital F of b minus capital F of a. So capital F of b minus capital F of a is equal to the integral, or the antiderivative, of some function lowercase f of x from a to b. This is often known as the fundamental theorem of calculus. And if you wanted to, you could, instead of saying f of b minus a, you could use what we call a bracket and say f of x, and then put b and a right there. Fun stuff. The fundamental theorem of integral calculus. Let's do an example. When we do an example, it'll make so much more sense. Find the definite integral of 2x plus 3, I mean 5x plus 2, from 3 to 4. Okay, so find the definite integral of 5x plus 2 from 3 to 4. Okay, so what this wants me to do is this wants me to integrate 5x plus 2 with respect to x, and I need to go from 3 to 4. So my upper bound is 4, and my lower bound is 3. And if you wanted to, sometimes it helps to call the integral I, but of course what we are finding is some change in an original function that we might want to call capital F of x. And we're doing that from b to a. I would just write I, because you know it's the integral, and later you can think about what this integral is. Okay, so the integral, 5x plus 2 from 4 to 3. How do I evaluate this? Well, first I need to take the antiderivative, and I'm going to get 5x squared, and then I divide that 5 by 2, plus 2x, plus c, my constant integration. Okay, so that's the antiderivative. But I still need to plug in 4 and then plug in 3 and subtract the 2. So what I do is I put this little bracket on the side and remind myself that I need to plug in 4 and plug in 3. So here's what that looks like. First, let's do the whole function and plug in 4. So 5 halves 4 squared plus 2 times 4 plus c. Okay, minus 5 halves times, not 2, 3 squared plus 2 times 3 plus c. Then I algebra. So this is going to give me 5 halves 4 squared plus 2 times 4 is 48 plus c. And then 5 halves times 3 squared plus 2 times 3 is 28.5, so minus 28.5, and this minus also gets distributed to that c, so minus c. Again, the c's cancel out. In fact, if you want, now that you know the c is always going to go away, don't include it. You usually don't have to include it in the work when you're using the fundamental theorem of integral calculus, and you would just do 48 minus 28.5 and get 19.5. So your definite integral is 19.5. Great. Congratulations. Now, let me show you a fun way to check to see if you did this correctly. First, let's get rid of some of this work. Actually, maybe let's leave the antiderivative. So 5 halves x squared plus 2, and then we evaluated from 4 to 3, equals 19.5. We'll leave that as our work. Let's remember that really what we're doing here is we are taking f of x, which would be a line that starts at 2 and has a positive slope, and we are finding the area from 3 to 4. And we are saying that this area represents 19.5. Well, if you use your graphing calculator, you can go to y equals, plug in 5x plus 2, 5x plus 2, graph it. Do I like that window? I don't know. Let's do zoom 6 to get our standard window. That looks better. Okay. So I graph 5x plus 2, straight line, great. If only there was some way for me to just quickly find that area from 3 to 4 under this curve in between the x-axis. If only there were some calculus functions in our graphing calculators? Well, if I press second, trace, which gives us the calculate functions, I might recognize a summa fx dx. And if I click enter, then I can do the lower limit, 3, press enter, the upper limit, 4, press enter, and boom, I got 19.5, the area under my function 5x plus 2. So that's a quick and easy way for me to find that area and evaluate that my answer is correct. Now, if I'm trying to show just minimal work, this is a great way to show minimal work. Most calculus teachers are going to want you to show a little bit more, but I think that this is pretty acceptable. Here, if you write I equals summa 5x2 dx from 3 to 4, this shows that you know the notation for definite integration. Then if you take the antiderivative, 5 halves x squared plus 2, and put this evaluation bar on the side, 4 to 3, then that means that you knew you had to take the antiderivative and evaluate it. And then at that point, you can go through the algebra if it's easy enough. Or often what I'll do is I'll skip that algebra part and I'll just go to my calculator and get this answer. And that's quite enough to justify my thought process. Okay, let's do this with a couple more problems. Okay, here we have find the definite integral of these functions from 5 to 7. So let's start with f of x. I'm going to say I equals, and then summa 6x squared plus 2x plus 3 dx. And I'm evaluating from 5 to 7, so 7 is my upper bound, and 5 is my lower bound. Okay, then I'll take the antiderivative, x cubed. 6 over 3 is 2. So 2x cubed plus, this is going to be x squared plus 3x. Remember, I don't need to add plus c because it's going to get canceled out after I do this evaluation from 5 to 7. Okay, now at this point I can plug in the numbers, but I'm just going to use my calculator to check what this answer is. So y equals 2x cubed plus x squared plus 3x. Oh, I'm sorry. I made a mistake. Oh, don't make this mistake that I just made. Everybody makes this mistake. Don't plug in the antiderivative. Plug in the original function. 6x squared plus 2x plus 3. The original function, not the antiderivative. Okay, then I graph it. Can kind of see it. And in order for me to do second calc, 7, or the integral function, press enter. Got to put in the lower limit, which is 5, then the upper limit, which is 7. And that gives me 466. So here I write 466. All right, let's do this next one. The indefinite integral of 4x squared plus 2 with respect to x from 5 to 7. I take the antiderivative, so this is going to give me x cubed, 4 divided by 3, plus 2x. Maybe I'll move this equal sign so that it makes more sense. Okay. I don't add plus c. Instead, I'm going to evaluate from 5 to 7. And I go to my calculator. Y equals, I don't put in the antiderivative. I put in the original function, 4x squared plus 2. Graph it. Go to second calc, 7. Lower limit is 5. Upper limit is 7. Boom. I found the area 294.6 repeating. So 294.6 repeating. And one more. Here I do the integral of negative t squared plus t plus 1. There are no x's in this, so I should write dt, because I'm going to do calculus to the variable that x is a function of. And I'm going to go from 5 to 7. So I take the antiderivative, negative 1/3 t cubed plus 1/2 t squared plus t. Then I put in my evaluation, go to my calculator. I'm going to write y equals, oh, not that, y equals, put in the original function, which in this case I'm using x instead of t, so I'd say negative x squared plus x plus 1. Graph it. And I'm going to evaluate second calc 7. My lower limit, second calc 7. My lower limit is 5. My upper limit is 7. Notice that this area is going to be negative because it's below the x-axis between the function. So a negative 58.6 repeating. And there are my answers to these 3 definite integrals. So definite integration gives you a number, and that number represents the change in some original function. Indefinite integration gives you an equation, and it has the constant of integration, c, in it, because you can't know that from taking the antiderivative. It has to be told to you. We call it the initial condition. Congratulations on this wonderfully long video that taught you quite a bit about definite integration. I definitely hope you get it. Bye.